Okay, so now let us look at the instruction format, because we are designing our computer. So we will anticipate the software programmers who are programming our computer to write program in a certain way which is understandable by our hardware, right? So our instructions are going to consist of 8 bits, right? We have also said that our memory is byte addressable, so every byte could either represent an 8-bit data or it can represent an 8-bit instruction. Okay, and an instruction is basically, as I told you earlier also, one quantum or one primitive operation that could be directly executed in hardware. It could be addition, it could be subtraction, whatever. It is the architect of the CPU who publishes the instruction set architecture to a software developer, saying that I offer this kind of facility in my CPU, right? So typically this is a part of the ISA, right? If you have forgotten what this ISA stands for, this is instruction set architecture. Okay, so the instruction set architecture is often called a contract in between the hardware and the software, right? So the hardware architect or the CPU designer gives a contract to the software programmer that this is my ISA. Your software that you are writing ultimately, right, whatever high level language you are using, you have to either actually use a target specific compiler, right? Because my compiler has to write machine code that the Gajendra-1 architecture CPU understands, right? Otherwise, a compiler that compiles for x86 target or some other RISC-V target is not going to work in this particular thing, right? Because they are going to have a different instruction format, right? Our hardware will not understand those things. Okay, although the rationale is the same, right? At the end of the day, maybe adding an immediate value of 5 to the accumulator can be done in any processor architecture, but the way the language, right, uh, of the hardware, the machine code is going to vary from architecture to architecture. It depends on the rather the micro architecture. Okay, how actually this instruction set architecture is implemented. Okay, so we are specifying this ISA to the software world, right? And we are going to implement this ISA, which is actually called a micro architecture. Note that this ISA can have various kinds of implementations. You can have multiple kinds of micro architectures for the same ISA. Somebody can have a better design in terms of hardware, but that is not going to change the ISA. So you have already studied a lot of software programming. You can think of this ISA like an API, right? So the API is a contract that the library designers might give you, that if you are trying to do this particular thing, you take my API, this is a function call, and this function call has these parameters, which is the signature of the function, and this is what you return, right? Or you get as a because you can call this function, this function provides you this and that, right? So this is a functional specification of the API code, right? But for the same thing, for the same API, you might have various implementations, like interface. You mentioned that this is an interface, but you can have a custom implementation of a certain interface or a certain API call. Okay, so somebody can have an efficient implementation, some other implementation might not be that efficient, and so on. Similarly, ISA is something that is exposed to the programmer or the software world. Microarchitecture is an instance of realizing that ISA on a specific design. It's a specific design. Okay, so hope you understand this term called ISA and you understand this term called microarchitecture, and we are designing or we are specifying a certain instruction set architecture. So now note that no, coming up with an ISA is also design work, right? It's not that you have to have this particular ISA. It depends on the kind of applications that your target CPU is going to run, right? So what kind of instructions make sense for the applications that are going to be run on the CPU is extremely important, right? So sometimes we even need it before designing, right? Because once you design the hardware, you are sort of done, right? So before that, you need to kind of understand that what kind of necessities or what kind of applications are going to be running on your CPU and what is their demand, right? What kind of operations do they do? Do they do a lot of floating point multiplication, or they are mostly going to do integer operations, or whether they are going to do any uh, mathematical computation at all? Maybe there is a lot of data transfer operations that are going to be done, right? So depending on that, you might be inspired to make your ISA flexible towards a certain class of applications, right? And this is really a design, right? So design, or I would say art, right? It might not be pure. It's not a scientific method that is going to tell you that, oh, this is the instruction set architecture that is going to be the optimal, right? There is nothing like that. You have to be, as a designer or an artist, you have to think that these are the kind of applications that might be supported in the CPU in the longer run, and if your CPU has to survive the application demands of the market, and I am providing the ISA for the market, okay? And similarly, you have to make sure that whatever ISA you have specified, you can implement that microarchitecture in a reasonable uh, way, right? Because of course there are constraints, right? The constraints could be the complexity of the circuit, the energy consumption of the circuit, the cost of the circuit, the size or the form factor of the circuit, right? Under all these constraints, you need to basically make sure that your ISA could be implemented, okay? So that's the design and the art part of it, right? So now coming back to our discussion of the Gajendra instruction format, we use the, out of the 8 bits, we use the first 4 bits or the most significant 4 bits to specify what is called the operation code or opcode. So this is also called operation, okay? So operation specifies that what typically what the ALU is going to do if it is not a data transfer instruction like move or store or load, right? Apart from those instructions, if it is an add or subtract, whatever, that operation is specified using these 4 bits, okay? So if I use these 4 bits in our Gajendra-1 instruction format, I could say that we can support up to 16 different operations, right? Because there are 4 bits, I can specify this bits, right, in 16 different ways. So I can say 0000 opcode, let's say, means something, right? 0001 means add, 0010 means subtract, 0011 means something move, right? Move A to B, right? At the same time, you get 4 more bits to uh, do some, provide some signature, right? So you can think of this as in a very constrained way, it's a hardware function call, right? So however you have thought about of APIs, what does the APIs do? The API have a signature, and that signature states that what are the uh, uh, parameters that you are passing to a function, and they also will have a return type and some kind of values that they are going to return, and that is what defines your function, right? Similarly here also you can think that your operation is the function, and the operands in some way are going to specify the parameters of the operation or the function, right? And sometimes, as I have told you earlier, because of the limitation in the number of bits in the instruction, you can't really put too many things as a part of the instruction, right? In software, you keep on defining that, okay, there are this many parameters and so on. Typically the limit is much higher, right? The number of parameters that you can pass, right? In this particular case, there is nothing but just raw bits that you need to pass as a part of the instruction. So here we are only having 4 bits. Okay, so you may have more, but in our case we are constrained by this 8-bit instruction format. In case we had a let's say a 16-bit instruction format, you could have done a little bit more, right? Of course addresses are going to take up a lot of it, because you often need to pass an address, right? Coming back to what I was saying earlier about the parameters, so because we are not able to pass a lot of these operand bits explicitly, sometimes there is an understanding of the return, let's say, location of the register or some of the source registers. There is an implicit assumption. Okay, so often many of these operations take one register, let's say register A, often called accumulator, as an implied source. Okay, so if I say add something, let's say add a number, let's say add 12, right? It is going to implicitly assume that it is going to add 12 to the value contained in the accumulator, and the result that you get, let's say A had a value of 8 earlier, now you are saying add 12, right? So 12 plus 8 is 20, right? So there are so many things that is being assumed. 12 is going to be added to the value contained in the accumulator, so it becomes 20, and the result is going to be stored in the accumulator itself. So the accumulator's value is going to be updated to 20. It was 8. Once you execute the instruction add 12, it becomes 20, right? It is not specified explicitly as a part of the instruction format. Okay, so sometimes the operands are there, these are the explicit operands, but there are many implicit operands. Okay, so still, if we want to mention something about that address, we can either use the last 4 bits to specify a 4-bit address, as you can see, A3, A2, A1, A0, or if I want to specify a certain data, I can also do that, right? So I want to add 12. 12 could be expressed as a binary number 1100, right? So this is an immediate data that I want my operation to use. Okay, so the last 4 bits in our Gajendra-1 instruction could either be used for specifying a 4-bit address or specifying a 4-bit immediate data. Okay, we are going to restrict ourselves to this, and real world examples I'm going to show you some. Intel x86 has very complicated instruction formats. I am going to give you an example of the AVR instruction set, which is another instruction set which is comparatively simpler, and you will see that what we are kind of teaching you is not something which is very outlandish. This is something, you can call it very simple, but this is how real world instructions even look like, right? You have some bits dedicated for opcode, you have some bits dedicated to the operand, and you have to read the instruction nomenclature in a certain way, and the hardware circuit, particularly the something called an instruction decoder, is going to be able to make sense out of it, right? So the hardware at the end of the day is going to make sense out of these 8 bits. That's the work of the hardware. Okay, so now coming to the example that I have just now promised is the AVR instruction set. Many of you might be knowing about this Atmega 328p microcontroller, because this is the microcontroller that powers these things like all these Arduino boards. Yeah, Arduino boards. Typically, people do all these IoT projects in your let's say BTech projects and so on. You often use this kind of devices. So and this is a very cheap microcontroller, right? It's called a microcontroller. It also has an integrated memory inside it, where you can load a program, and it's typically called flashing a program, and the program is going to be run in the CPU. It has an internal CPU also. So it's a microprocessor with a integrated memory. So it does have a CPU. So there is a CPU inside it. There is also a memory module inside it, which is going to be loaded with your program. And then there are other components that I am not going to talk about. There are peripherals and so on for uh, analog to digital conversion. You can attach sensors and all. So that is not a part of our discussion in this particular class. We are going to concentrate on the CPU, and as you can see that there are 131 powerful instructions. Okay, and this chip might cost you only 100 or 200 rupees maximum in the market, right? I'm not talking about the Arduino board, right? Rather the microcontroller itself, which is powering the board, right, is much cheaper. This is something even this is very complicated, right? As you can see, it can support up to 131 instructions, and often they are single clock cycle execution. We are not even talking about single clock cycle execution. We are typically looking into an instruction that can take multiple clock cycles to execute. So even in comparison to this kind of a processor, we are way behind. Probably you can understand what this means. 32 into 8 general purpose working registers. I have already told you about a concept called a register file. A register file inside a CPU contains a collection of registers. Okay. In our Gajendra-1 architecture, we are only having 3 registers A, B, and C, as I told you. A, B, and C. So 3 into 8 general purpose register. 8 stands for 8 bits. So this is the number of registers, and this is the size. For us also it is a byte, right? It's 8-bit register. I am also going to talk about this thing, right? So since it is a single clock cycle execution that is happening for most of the instructions, so if the processor is being clocked at 20 megahertz, it is going to execute 20 million instructions per second, because 20 M stands for 20 million, right? 20 mega. So if most of the instructions are taking only one clock cycle, you can get a throughput of 20 million instructions per second being executed on the CPU. Here throughput is not a network throughput, right? It's basically the number of instructions that could be executed on the CPU per unit time. Okay, and they have some special, as I told you, many processor designers might have things that they can boast about. So they have a on-chip 2-cycle multiplier, right? So they have clearly stated that, see, we have a multiplication operation. So this is your ISA, right? Suppose I am looking for a CPU that supports a multiplication, right? Maybe there are other CPUs in the market which are kind of similar in price range, but they do not have a multiplication operation. And I found out this CPU that, okay, they have an interesting feature they want to kind of talk about, which is multiplication, and my application might be requiring multiplication a lot, right, compared to other kinds of instructions. So this is something that you should then buy, right? So in this particular instruction set architecture, they have specified a multiplication instruction, and they clearly say that it is going to require 2 cycle. Okay, so this is how you can take a look at this instruction manual. You can just skim through it, and it is going to give you an overall feel of processor. right, and the various features inside a processor. Okay, of course, not into great details. I'm simply talking about a superficial understanding of the various features that a processor might have. Some of them has been like here, right? So now you understand what is an instruction. The instruction set architecture is going to have 131 such instructions. You know what is meant by a clock cycle. You know what is a general purpose working register. You know what is let's say million instructions per second. So sometimes MIPS is also quoted to know the performance of a processor, how many millions of instructions per second they are going to execute. Okay, so 50 MIPS means 50 million instructions per second, 10 MIPS means 10 million instructions per second, more the better. Okay, so I am going to take you through some real world instructions, right? So they are all having the 16-bit opcodes. So this opcode again is uh, sometime interchangeably used. So here 16-bit opcode, they are trying to say that 16-bit instruction code. Okay, so as I told you in this previous slide, I told you an 8-bit instruction format. They are talking about a 16-bit instruction format. Here in my case, I have spoken about an opcode, which basically means the operation code, right? Just the first 4 bits. So there is a minor difference, and this difference is going to be there. I mean, as you look into more and more literature, sometimes the opcode is just going to tell you the exact operation, and the other one is an operand, and the entire thing is going to be called an instruction. Whereas in this case, this document called the entire instruction to be an opcode. So you just clarify what exactly is given to you. Okay, so the entire thing is called an opcode. It has 16 bits, and as you can understand that what this is about, this is a load immediate instruction. So it says that this instruction loads an 8-bit constant directly to register 16 to 31. Okay, so you have to basically load a 8-bit number, because these registers cannot hold anything which is more than 8 bits, because the registers have a capacity of a byte. These are byte registers, and LDI is load. Fine, load basically means that you are going to load a register, but not from memory. You can actually have a load instruction where it loads the register from memory, but here you are trying to directly initialize the register with a particular value, which is called load immediate. Okay, so the load immediate is going to use how many bits? Let us see. You are going to initialize the register with a 8-bit constant, so that value can be only from 0 to 255. So 8 bits for the operand, right? And as you can see, the instruction operation is this, right? RD is your destination register. Okay, RD is destination register, and RD is going to have an address, and K has 8 bits. They are going to specify the immediate value. Okay, and then D is the destination register's address, and D is going to vary from 16 to 31. Okay, so here what you need to be careful about is that how many bits are dedicated, right? So if you look at the manual, they are going to talk about it more. So you are having only 4 bits. Okay, because we are not really referring to all the registers from 0 to 31, right? Because that will require you to have 5 bits. So because we want to pack uh, as many bits as possible, because first of all, this thing itself could mean that this is a load operation. Then we have to save some number of bits for having this 8-bit the 8-bit immediate value. So 8-bit is gone here. So 4 here and 4 here. So we are only left with 4 bits, because 4 plus 4, 8 is gone for the immediate value, 4 is gone for the load, and only 4 is there. So I cannot directly register 0, directly refer to 0 to 31, not possible, because I only have 4 bits, I don't have 5 bits. If I need to do that, then I will need a 17 bit opcode, which is not possible. I mean, we are specifying only a 16 bit opcode, right? So we are forced to use only 4 bits, and these 4 bits could be starting from 16, right? It could be 1 0 0 0 0, right? uh, which is 16, to 31, which could be 1 1 1 1 1. Okay, and instead of using, this is redundant because this is always going to be 1, right? We can just specify the least significant 4 bits, which is d d d d, right? And it will achieve this job, right? To give you an example, let's say I want to load register, let's say 23 with a value, let's say 14. Okay, so if I want to have this instruction LDI, I said register number 23, so R23, and we are going to uh, load this with a constant 14. Okay, so 14 is decimal, or you can, it is up to us how we want to define, but this is what we want to follow the syntax, right? So let's say this 14 is base 10, so I can always convert this. So if I want to write the machine code for this LDI R2314, what is going to be the machine code for this in this opcode format, right, in this ISA? So definitely the first 4 bits are going to be 1100, 1110. So this specifies that this is load immediate, rather load immediate. Then I have next 4 bit is KK, then the last 4 bit is also KK, right? So 14 is 1, 8 plus 6, right? So 1110, right? This is 14, but we want to use 8 bits, right? So this is your 14 value, right? So this is 14 to the base 10 is equal to this to the base 2. Okay, so the first k, of course there is a description, more description to this particular uh, content of the text that I have shown. They will definitely specify this first 4k is the most significant or the least significant, assuming that this first 4 bits here is the most significant MSB4, right? Most significant 4 bits. It is going to be 0000, and the last 4 bits are going to be 1110. So these are the first 4 bits. They go. This is your KKKK, one set, and this one is again another KKKK. The last 4 bits. Okay. Now comes 23. Okay, so this one and this one in a combined way could express a 8-bit value equal to 14 in decimal form. Okay, now remains the third nibble, which is I want to express the destination register 23. What is 23? 23 is again 16 plus 7, so 16 plus 7. Okay, I think this should be 23. Yes, and here, as I initially told, that this is going to be redundant, right? Because anything starting from 16 is going to have 1 as the most significant bit, up to 31. Everything is going to have the this bit, right? 0th, 1, 2, 3, and fourth significant bit is going to be 1. So we are going to have this value as 0 1 1 1. Okay, so if you think of the 16-bit word or the opcode in machine language, this is going to be because it is hexadecimal, I am going to specify this in hexadecimal format, 0x. Now let me write the binary values. So load, as you can see, this is you have the first most significant bit is 1. So right, so this is E. If you see 1 1 1 0, so this is 14, right? So this is E. Then there is a 0, right? Then there is a 7. Then there is a E again. Okay, so if you write E07E, the processor is going to load the value of decimal 14 to register 23. This is how a assembly level code is converted to machine code. So this is the machine code for LDI R23, 14. Okay, or you can write LDI R23, 0xe. Same thing. Okay, so rather you should write 0x0e because it is going to support 8 bits. So ideally you should provide 8 bits, right? Where the first 4, like most significant 4 bits is 0, right? So this is typically the task of an assembler. So there is a program called assembler which takes your assembly code, right, and pops out the machine code. Okay, so often you will look at this programs called disassemblers. So people who want to crack software, they want to see that what a particular software is doing with a password, or they want to recover some password, will come across of any sort of cracking videos where they will take an executable and that executable is going to be disassembled. So once you know for what architecture the executable is, if you give that target architecture where this is supposed to run to the disassembler, this is going to pop out a series of instructions, and then you have to do all your detective work on the instruction set as well as the program to figure out what this program is really trying to do. Okay, so we are not going into that business, it is just a side note that I have kind of told you. So any instruction is going to be likewise converted to the machine code. And for Gajendra-1 architecture, what we are going to do, we are not really, we are going to do the work of the assembler manually by hand, the way we have done it right now. And for us, it is more simple. We are not going to have a 16-bit opcode. We are going to have a 8-bit instruction format. So even it is more synced up, right? And our memory cannot hold 16, it's not a 16-bit addressable, it's a 8-bit addressable or byte addressable. So we are only going to have two such nibbles, right? Two 4-bit as a way to express an instruction. Okay, so we'll go through 2 or 3 more examples of again AVR architecture. This was example 1.